Hello everybody, welcome back to Advanced Maths. Today we're looking at conceptual understanding. And this is mainly pitched at maths teachers. However, general educators will also have an interest in this. Parents would have an interest in the idea of conceptual understanding because you care about your son or daughter's education. And students might find this interesting as well about what you're trying to aim for in education. So conceptual understanding really underpins what we're trying to do in learning. We're trying to form deep understanding somehow. And I'm going to talk to you a little bit about what that really means. So I am Will McLaughlin. I am the creator of Advanced Maths. I'm studying a doctorate in education, and this is really informing what I'm going to talk about today because a lot of my studies and research revolve around this subject. And if you're interested in the discussion, please email advancedmaths@gmail.com. Or please get involved in the discussion and comments below. I'm really interested in your thoughts. And if you're interested in more reading about conceptual understanding, I've got the link to the website with some research papers on conceptual understanding for you to read. And those research papers largely are the research base that informs today's video. So if you're interested in my sources of why I've said some things, check that out. That's probably a good place to fact check me, if you will. Okay, so let's start with thinking about what conceptual understanding actually is. So conceptual understanding is defined as deeper, comprehensive, and connected knowledge of the abstract ideas in a domain, which enables novel thinking, problem solving, or learning. And this definition was me in 2023, trying to think of a definition that brought together lots of different ideas from different people about what conceptual understanding really is. Not everyone would agree with that definition. It is my definition. It's not from the dictionary. But some of the big ideas in this definition we will explore more and more in today's video. So, let's continue. And one of the, just to underline one of the key points here is that we are connecting knowledge. So the idea of connected knowledge. And we start with knowledge, just learning individual facts. And these facts might not be connected. They might just be weird, unconnected facts that students don't really understand. But the job of us educators is to then draw these facts together, and we then start to make connections between the facts. And slowly you get just a small web of facts joining together, so that you get connected ideas coming together. And this diagram on the right is an example of what we're kind of aiming for. We're aiming for all the different facts to be really easily connected so that the brain makes these connections easily when they need it. Now, this kind of diagram on the screen is called a schema diagram, and we'll be using that later in this video as well. So just addressing this now, this is kind of a very abstract way of imagining the brain holding knowledge and then making connections between knowledge, which I'm saying is probably a good way of learning. And also it supports long-term knowledge retention as well. The idea of connecting knowledge pieces together helps make those individual pieces of knowledge more durable in memory to last longer. Okay, so let's talk about the knowledge spectrum. And this is derived from Riddle, Johnson and Siegel's 2001 article. They've also written some other articles more recently that are all worth reading, some fantastic research in the field. So we start on the left with declarative knowledge, and these are just rote-learned facts. And these facts can be declared without conscious active processing. For example, if I asked you what 15 plus 5 was, most of you would just instantly say 20. What is 3 times 7? a lot of you, without really thinking, without having to actively engage your brain, would just know 21. And this is declarative facts that just your brain doesn't really have to be active in figuring this out. And a key idea I want to communicate today is that this is actually good. And the myth that memorizing your times tables is contrary to conceptual understanding is quite damaging, because actually rote learned facts does support later mathematical thinking, and that's necessary for developing conceptual understanding. After declarative knowledge, we've got procedural knowledge, and this is knowledge of algorithms or procedures, and this needs to be practiced. This needs to be really, really practiced to get good at, because it's actually quite complicated. And Rittel, Johnson and Siegler said this was the ability to execute action sequences. It's just following a set of steps in maths, like a recipe for adding fractions or something like that. And this is also very useful. This is absolutely essential to be able to follow mathematical procedures, because that's an inherent part of maths as a subject. And then on this side, we've got the conceptual knowledge, and this is really connected. This is what my definition from the previous slide was talking about. And it's this idea that you've connected ideas together, you've connected declarative knowledge together, you've connected procedures together, and now you have a deeper understanding of the field, the domain. And what I'm trying to show on this slide is that all of these types of knowledge, declarative, procedural, and conceptual, are all part of the same spectrum. And what they definitely not are is they're definitely not conflicting. And some people in the past have argued that declarative knowledge is contrary to conceptual knowledge, and that's doesn't seem to be in line with our best evidence. In fact, our best evidence is that developing conceptual understanding and procedural skills is an iterative process, a process where you get slightly better at one of those skills and it supports the other one getting better. So you might get better at procedural fraction addition, and that helps you understand the deeper ideas of what is happening when you're adding fractions. And that slightly deeper understanding of adding fractions helps you get better at adding more complicated fractions. And then that supports an even deeper understanding of fractions as well. So this idea that procedural, declarative, and conceptual understanding all support each other, and you have to get better at all three at the same time. And it's an iterative process. That idea of it's an iterative process. Getting better at one supports getting better at the other. So this is a mutually supportive and iterative spectrum. And I've said at the bottom, strong declarative knowledge supports procedural understanding, which in turn supports conceptual understanding, and vice versa. And if you'd like to understand why this is, a really clear idea of why this is an inherent part of human cognitive activity, I would implore you to study cognitive load theory. And that's outside the scope of today's video. Let me know in the comments if you'd like me to do another video on cognitive load theory. I absolutely love it. It's really interesting. But that theory helps you understand why the human brain works like this. It helps you understand how the human brain processes mathematical information. So yes, and if you are interested, check out advancedmaths.com/CLT. Okay, anyway, continuing. So why do we bother with conceptual understanding? And basically, if you're interested, this is a really interesting justification that I read. It's this idea that there's a problem with human thinking, in that we really struggle with transfer. Transfer is this ability to apply knowledge in one context different from the context it was learnt. So you might learn an idea in a maths classroom and then really struggle to apply it in a physics, economics, or psychology classroom. Because the context is different. You're transferring to a different context. And if you want to read more about this, check out Barnett and Sessi's paper. Absolutely fantastic reads. But basically, anyway, what I'm saying is that deeper connected knowledge of conceptual understanding helps you transfer ideas to other contexts, and that means you're better at problem solving or application. And that's why conceptual knowledge is actually very good. And of course, that will help in those trickier exam style questions. Now, just coming back to my definition here, conceptual understanding is defined as deeper, comprehensive, and connected knowledge of the abstract ideas in a domain, which enables novel thinking, problem solving, or learning. I want to emphasize this idea of enables. It enables novel thinking, new ways of thinking. It enables problem solving, and crucially, it enables future learning, because you have a deeper understanding of things, and that means you can build on that knowledge easier in the next lesson. And while we're on the idea of why, I've just got some key ideas that came to mind of why conceptual understanding is actually really beneficial in education. And we'll just go around. We're less likely to have misconceptions, so bad ideas are less likely to last, because all these connected pieces of knowledge are more likely to be in conflict, in cognitive conflict with the misconceptions. So the good ideas are in conflict with the bad ideas, and that's stronger if you've got conceptual understanding. Students have stronger and more durable memories, and that means that retrieval strength and storage strength is higher. Which is, if you've read anything about retrieval practice or the Bjork's work on memory, you will know that memory is incredibly important for learning. In fact, that's the whole point of learning, is to change our long-term memory. It's easy to build future learning on good current learning. And that means that you get a really good prior knowledge for your future learning, to connect more ideas to in the future. Now, we've also talked about the deep structure of problems. So when you come across an exam style question, and that exam question perhaps has a hidden triangle that you have to do Pythagoras theorem on, you're more likely to notice that triangle. Say it was a ladder against a wall, and you have to figure out how high up the wall the ladder goes. Well, you're more likely to recognise that as a right angled triangle problem if you can see the deeper structure, which I think is enabled by conceptual understanding. And finally, something that I forgot about in the past and I really want to emphasise today is conceptual understanding is really good for motivation. Students realise they can understand this. They are capable of understanding maths. And if we aim for that, that's incredibly encouraging and motivating for students. And it's a form of intrinsic motivation that is really fulfilling and rewarding. So yes, that's why I think conceptual understanding is so important. Now, this is the important part. These are the strategies I suggest for the classroom of how to enable conceptual understanding. So let's start with explicit instruction. And this means that we teach students explicitly and clearly all mathematical concepts. And that means that we're not withholding any information. We are making it as clear as possible for students to understand what's going on. And this is in conflict with the idea that students should discover maths themselves, or inquire, or go on long research projects. And in my view, as I've understood the research, and I think I've read it quite well, inquiry-based learning or project-based learning is actually quite detrimental for conceptual understanding. And there is some debate about this, but I think the research is quite clear. And if you're interested in the research, again, go visit cognitive load theory. Cognitive load theory is very clear on why explicit, clear guidance is superior to less guidance from a teacher. And this looks like lots of worked examples, lots of questioning and formative assessment, and scaffolding in the classroom. The teacher is really doing all they can to support students in processing the ideas that are being presented to them. And yes, this is just good teaching. This is what most good teaching frameworks advocate. And so there's nothing new here, but this absolutely does lead to conceptual understanding. And I've said at the bottom, we need to scaffold new topics. So we're not just doing a big worked example that confuses students straight away. We're kind of building up to that, we're scaffolding towards it. And then, once we've kind of explained all the steps, given a bit of mini whiteboard practice, we eventually lead to students doing lots of independent practice of the procedures, of the declarative knowledge, and building up to the conceptual knowledge. And, extended periods of silent, independent practice in maths classes is good, is effective, and recommended. Now, variation theory. Subtly altering questions that you are giving students enables them to start making connections between different questions. And it helps them perceive a deeper mathematical structure. And if you're interested in a bit more of this, go to variationtheory.com. This is from Craig Barton, a fantastic maths teacher from the UK who is really good at communicating pedagogy. But if you like to get a taste of what this looks like, I would recommend you pause the video now and have a go at finding the mean of the 3 sets of numbers at the bottom of this page. Pause the video now and have a go at that. Okay. Now I'll leave it to you to think about what you noticed. How does the first question relate to the second question? And how does the second question relate to the third question? And what kind of rich discussions could you have with students once they start noticing these patterns? And then, how can you lead this into talking about what the mean actually means? What does average represent in maths? And help students understand what the mean represents when we work it out. Check out variationtheory.com. It's a fantastic set of resources on there. Now, self-explanations. This is the idea that we are asking students to explain ideas to themselves. Explain it to yourself. And I quite often do this, especially with my oldest classes. I pause a worked example after a step and say, look at the step I just did. Look, it's right there. And I point to it. And I say, take a moment now to think about why I did that step. What did it achieve? Pardon me. And that is a little bit of a prompt for active cognitive processing of what we're talking about. Because, as we know, students are lazy and they prefer to just sit back and not think about what we're doing. But quite often these prompts do help. Now, I kind of recommend that mature self-explanation, independent work for the older age groups, year 11, year 12, or year 13. However, if you've got younger age groups, you might want to do something a bit more clear and obvious, like a think, pair, share routine. And this is a really practical strategy for this. And think, pair, share can be quite tricky to do well, and I'm not the person to tell you how to do a perfect think, pair, share. However, if you look at some other resources online, probably Craig Barton's Tips for Teachers podcast is really good at talking through how to do a really good think, pair, share routine in class to ensure that every student in the class then is thinking about the right thing and explaining to their partner the right kind of idea. Self-explanations are really good. They are supported by the research, and what we find is that when students self-explain ideas, they have a deeply conceptual understanding. This is also good revision advice if you're revising and reading through some ideas. You need to pause, read through what you just did, and make it make sense in your own head. That is a phrase I use in class. Make it make sense to you. Make it make sense. Now, retrieval practice, this is a really interesting one. And this retrieval practice is talked about a lot in education, and it's incredibly powerful. It's probably the least controversial cognitive science idea there is, because the evidence is just so strong and so repetitive and so clear from the experiments that retrieval practice is incredibly powerful for learning. And this is the idea that students have to search their own long-term memories for the relevant information and apply it in their own independent practice in that moment. And this normally looks like a starter at the start of class, but it also can be the independent practice during class time. And students have to search their ideas and find those memories or ideas they just made and use them in the moment. And this strengthens the memory long term. And the more you do this, the more likely that memory is to be easy to access in the future. But crucially for conceptual understanding, this re-encodes the memory in the new current context. And this strengthens the current connections while also making new connections with other ideas in long-term memory. And so retrieval practice is quite often overlooked in maths education in terms of conceptual understanding. You know, we talk a lot about it in terms of memory, but actually a deep understanding through retrieval practice isn't talked about as much, but I think is really, really promising. Now, remember, factual and procedural knowledge supports conceptual knowledge. So we've talked about that. And if you still don't believe me on that one, I would recommend you read Rittel Johnson-Ziegler's paper that I linked at the start of this video. So strengthening factual and procedural knowledge through retrieval practice is going to make things easier. And again, this is about making the demands on working memory easier and lighter, and that comes from cognitive load theory if you're interested. And crucially, rote learning is good. And don't be afraid to insist on drill practice during maths class. And I've put a little chili emoji next to that because it is quite a spicy take. It's quite controversial to say that, and I recognise that. However, I stand by it. And those people who say, don't do drill practice because it's bad for the kids, I'm sorry, I really must disagree. If you want kids to become proficient in maths, to take on the demands of the real world, which is absolutely essential for a huge number of careers, I would argue every career, you need to have maths facts straight away. Another idea is that in the age of AI, we don't need to learn the times tables anymore, things like this, because we can just Google or ChatGPT 7 times 8. Well, I massively disagree, because to understand what ChatGPT is telling us and the information it's telling us, we need to be able to process it in the moment in our own heads. And we can't just endlessly ask ChatGPT to simplify what it's saying. Because we'll never actually understand what it's saying, and we'll never be able to make judgments about what it's saying. And so we need, in our own heads, some way of processing mathematical information that it gives us. And that comes from rote learning. Anyway, enough about that. Let's move on. So what does this all look like in practice? And I'm going to try and give you a bit of a clear idea of how we will plan a set of lessons based on these ideas. And on the left, I've got the timeline, I've got lesson 1, and on the right, I'm going to draw a schema diagram similar to I did earlier in this presentation of what we can try to build up over time. And we're going to start with prior knowledge, and I've got a little circle here with PK next to it, PK meaning prior knowledge. And that's what we're going to start with. We're going to start lesson 1 with some level of prior knowledge. Probably a good idea just to check that prior knowledge exists with a starter and some formative assessment, probably on mini whiteboards, because we want to check the entire class all at the same time. And we're going to connect prior knowledge to our first concept. We'll call our first concept Concept 1. Later in the lesson, we'll also introduce Concept 2, and we'll try to connect all 3 of these together with one of the strategies, or a combination of strategies that we'll learn today. And we might also touch on Concept 3 today, but it might be quite a weak connection, which we might have to strengthen later. And let's just zoom in here and look at our cognitive schema diagram. So here we have the connections between prior knowledge, Concept 1, Concept 2, and Concept 3. And let's have a look at what this might look like. And we're going to start with prior knowledge, and we're going to make sure we activate it. We're going to ensure that the prerequisite skills and knowledge that is needed to understand what we're going to talk about in today's lesson is ready on the tip of our tongue, really clear in our minds. And normally this is the starter of the lesson. This is a do now activity. But you might also just make sure that the entire class understands specific ideas with a little bit of rapid fire mini whiteboard questions. Now, if you are hitting concerns here and the students do not have the prior knowledge, my best recommendation is to pause your lesson plan and to address that, and maybe even spend an extended part of this lesson dealing with prior knowledge, because it's not going to be very effective if you push on with new content while there are gaps in previous content. So we've dealt with prior knowledge. Now we're going to do a worked example to deal with Concept 1. And we're going to show Concept 1 as a set of procedures and concepts. Now, you need to pitch this worked example so it's not overwhelming to students. You need to scaffold it accordingly. And I would recommend using the I do, we do, you do routine, where I, as a teacher, start by showing the steps. Then we do a we do, where the class help me with one of the steps. You know, it's gradually fading towards the students doing a little bit more. And then eventually, I want to see the entire class do the full worked example on their mini whiteboards. So it's fading from completely my control to entirely the student's control. Furthermore, I'm really excited by Chris Bolton's work on unstoppable learning and this idea of atomization. And I would really encourage you to listen to his podcast with Craig Barton about atomization. It's not my expertise, but I think this will be very helpful ideas to better understanding how to make worked examples more conceptual in nature. Now we might also address Concept 2. Concept 2 might not be a procedure, but it might be a diagram or a manipulation you can do with the ideas. And this might be well achieved through a teacher-drawn diagram on the whiteboard, a manipulative, or an animation. And it's up to you to choose what is most appropriate for students in that context. And when you're doing this, you really need to guide attention to what they're focusing on. Explicitly point to key ideas. Highlight it if you can. Because you want students' attention focusing on the right thing so they can process the exact concept you're focusing on. Because I promise you, if you give them manipulatives or a fancy animation, they could be focusing on anything and get very easily confused if you're not very clear about what you want them to guide their attention towards. Now, connecting concept 1 to concept 2 could be a self-explanation prompt, and you might put the two concepts side by side and try to connect them by asking questions like, what do you notice? Alternatively, you might use variation theory to draw these two concepts together. And then concept 1 and 3 could be connected by a worked example again. And that might be lesson 1. I might be even too much for lesson 1, but that's a rough idea of what we're trying to do in the first lesson. Now, that's lesson 1, but look at the diagram carefully as we move to lesson 2. Look at the schema diagram as we move to lesson 2. And we see that it's faded. Memories have faded. As I'm sure you're familiar with as a teacher or as a student, as time goes by, our memories just fade away very, very quickly. And that's a shame, and that needs addressing. And so it's absolutely essential that we recap with explicit teacher guidance and retrieval practice to strengthen these memories. And so what we get is a stronger schema diagram where the memories are, and the concepts are connected stronger together. And in lesson 2, I think it's probably best to try and connect all of the ideas together in some sort of explicit way. Now, also remember that consolidation through lots of independent practice is really important here. And so you absolutely would give students a worksheet to work through in silence for at least 10 to 20 minutes of this lesson. I would push it to 30 if possible. Independent practice is so important. And we might also, in lesson 2, connect lesson concept 4, and we might start to build up more and more parts of our schema diagram. And now we can consider this diagram here as one connected piece of knowledge. And we could even call this in itself one single schema. And that now forms our prior knowledge for lesson 3. And lesson 3 now starts to get to concept 5 and concept 6 through worked examples, self-explanations, or variation theory, or retrieval practice, however you want to do it, like that. And that will now form the basis of lesson 4 and lesson 5, etc. So what we're trying to do is build concepts together over time through our strategies. So, key takeaways from today's presentation. Conceptual understanding is about making connections between mathematical ideas, facts and procedures. And as I say, declarative, procedural and conceptual knowledge are all good. They are all necessary and they all support each other. The conceptual understanding supports future learning. It makes future learning easier. Durable, lasting memories. It makes memories more likely to stay and not fade. Conceptual understanding helps with problem solving and it helps transfer to new contexts. It combats misconceptions and it's really good for motivation. And remember to tell students that I'm so proud of you for understanding the complicated idea I just talked about. This is really good. And strategies for this will be explicit instruction, variation theory, self-explanations, and retrieval practice. I would also just mention there that part of explicit instruction is just good teaching. Remember that all of your classroom routines need to be smooth, every student in the class needs to be focused, behaviour needs to be on point. So a big part of this is just getting your classroom practice really sharp. Something I'm always working on. I'm nowhere near perfect, but that's what we're working on. And it's just good teaching. I'm really interested in your ideas though. What would you recommend as good strategies for conceptual understanding? Let me know in the comments below. Now, I've been Will McLaughlin. I create advanced maths and I'm studying a doctorate in education, largely focused on conceptual understanding. If you are interested in reading more, check out my page on conceptual research. It's none of my research yet. I've not published my thesis. However, it gives you an idea of a lot of the papers that inspired today's video. Now, just to finish on, I'm really interested in your comments below. Let me know your questions, debates, and critiques below in the comments. If there's something I've said today that is controversial and you disagree with, please let me know in the comments below. I'm really interested in discussing this with you. It doesn't need to be a unpleasant debate. We can have a very convivial, lovely debate in the comments. I absolutely love having these discussions about pedagogy. It is fascinating. What is your definition of conceptual understanding? Let me know below. How would you reword my definition? And crucially, what strategies did I miss? As I say, I want to hear what you do in your class to enable conceptual understanding. Subscribe below as well and to support the channel, and I would really appreciate a like on this video. Thank you so much for listening and have a fantastic day.